So far, we've been concerned with descriptive statistics, numerical summaries of data. But in addition to describing data, we can use quantitative information to draw conclusions about the world, inferential statistics. A crucial concept in inferential statistics is uncertainty. Uncertainty in how the next election will turn out, uncertainty in how long before you'll need a new computer, uncertainty in the major of a randomly selected student. In fact, you could say that all of inferential statistics was developed to manage uncertainty in a reasonable, disciplined way. Uncertainty occurs when there's more than one possible thing that could be true. For example, it might rain today, or it might not. I'm uncertain about whether it will rain. How uncertain I am about the rain will depend on what other information I have. If the sky is overcast with heavy, dark clouds, even though I'm not certain that it will rain today certainly seems more plausible than not. On the other hand, if there isn't a cloud in the sky, I might feel fairly confident that I can go out without getting wet, though I might not be completely sure, as unexpected storms do roll in from time to time. Since we may feel that some outcomes are more plausible than others, it's helpful to have a measure of the plausibility of an outcome. We call this probability. Probability is a measure of the plausibility of an outcome, and it's symbolized, for example, by this symbol here, P, and then in parentheses, X/B. We read this as the probability of outcome X given our background information B. For example, we can talk about the probability that it will rain today given that the sky is overcast. In this example, the outcome X is it rains today, and our background information B is the sky is overcast. Probabilities are numbers between 0 and 1, and larger probabilities mean that an outcome is more plausible. A probability of 1 means that given your background information, you believe that the outcome must certainly be true. For example, the probability that the sun will rise tomorrow, given your experience every day for your entire life, is 1. You're certain that it will happen. A probability of 0 means that given your background information, you believe that the outcome must certainly be false. For example, given all the time we've spent together in class, the probability that your statistics professor is an extraterrestrial from Alpha Centauri is 0. You do believe that's impossible, right? Wait, don't tell me. Probabilities of 0 and 1 are both types of certainty. Certainty that something is true or certainty that something is false. Probabilities in between represent different degrees of uncertainty. If the probability is close to 1, you think more likely than not that the outcome is true, but it's not certain. And if the probability is close to 0, you think that more likely than not the outcome is false, but it's not certain. For example, the probability that it will rain soon, given that the sky is dark with heavy clouds, is somewhat close to 1. There's a good chance that it will rain, though you can't be certain. On the other hand, the probability that it will rain soon, given that the sky is completely clear, is fairly close to 0. It's pretty implausible that it would rain soon without any dark clouds, but it isn't completely certain because rain clouds could roll in pretty quickly. If probabilities of 0 and 1 represent complete certainty, you might wonder, what probability represents complete uncertainty? The answer is, it depends on how many outcomes are possible. The outcome space, or the sample space, is the set of all possible outcomes of a given phenomenon. For example, we could think about flipping a coin. We could get a head or a tail. Or if we roll a fair 6-sided die, then we could get a 1, a 2, a 3, a 4, a 5, or a 6. Or we could think about drawing a card from a poker deck. We could get the ace of hearts, the 2 of hearts, all the way up to the king of hearts, the ace of spades, and so on and so on. Or we could think about whether it's going to rain. It might rain today, or it might not rain today. There are 2 possible outcomes. In addition to thinking about just whether it rains, we could think about how much it rains. Here the sample space would be non-negative numbers like 0 inches, a half an inch, 1 inch, 1 1/4 inch, and so forth. We call a listing of all of the possible outcomes alongside their associated probabilities a probability distribution. This is the set of probabilities for each of the possible outcomes. The probabilities in a probability distribution will always sum to 1 because it's certain that one of the outcomes must happen. Otherwise, you haven't listed all of the possible outcomes. Now back to our question. What kind of probability represents complete uncertainty? If you're completely uncertain about what the outcome might be, you have no reason to believe that one outcome is more plausible than any other. For example, in a coin flip, you have no reason to believe that heads is more plausible than tails for the next coin flip. Or if you have a hat with 10 names in it, and you reach in without looking and pull out one of the names, you have no reason to believe that any one of the names is more plausible than the next. Probabilities are most uncertain when all outcomes are equally plausible. This is called a uniform probability distribution. This is a probability distribution in which all of the outcomes are equally plausible. That means that all of the outcomes are going to have the same probability. In particular, the probability of each outcome is going to be 1 divided by the number of possible outcomes, or that's the same thing as saying 1 divided by the size of the sample space. So we can think about a coin flip. The probability of getting a head, given that we have a fair coin, is the same as the probability of getting a tail, given that we have a fair coin. Namely, it's 1 out of 2. There are 2 outcomes, so the probability of each is 1 over 2. Or if we think about a die roll, the probability of getting a 1, given that we have an unweighted 6-sided die, is the same as the probability of getting a 2, or the same as the probability of getting a 3, a 4, a 5, or a 6. All of these are 1 divided by the number of possible outcomes, namely 6, 1/6. Or we can think about pulling a name out of a hat. Suppose we have 5 names in the hat: Roy, Grace, Andy, Abby, and Michael. The probability of pulling out Roy, given that we have these 5 names in the hat, is the same as the probability of getting Grace, or Michael, or Abby. It's all 1 out of the number of outcomes that we have in this sample space, namely 1 out of 5. What do we do if we're interested in more than one possible outcome at once? We can call this an event. An event is a collection of possible outcomes. It's a part of the sample space. It could be a very small part, just one outcome, or it could be a very large part, including the whole sample space, or anything in between. For example, if we're talking about rolling a 6-sided die, we could think about the event of rolling an even number, that is, an outcome of a 2, a 4, or a 6. Or if we're flipping a coin, we could think of the outcome of just flipping a head. Or if we're drawing a card from a shuffled poker deck, we could think about the outcome of drawing a face card, any one of these cards that has a face on it. The probability of an event is the sum of the probabilities of each of the outcomes in the event. For events that come from a uniform probability distribution, remember that's one in which each outcome has the same probability, the sum of these probabilities is going to be the same as the number of outcomes in the event divided by the number of outcomes in the sample space. For example, if we're flipping a head, then there's 1 outcome in our event, there are 2 outcomes in the sample space, and so our probability of flipping a head is 1 over 2. Or if we're rolling a number divisible by 3 using a 6-sided die, there are 2 possible numbers that are divisible by 3, 3 and 6. So there are 2 outcomes in our event and 6 outcomes in the sample space. So the probability of rolling a number divisible by 3, given that we're rolling a fair 6-sided die, is 2 out of 6, or 1 out of 3. Or if we're drawing cards from a poker deck, we could think about drawing a face card. Here there are 12 possible face cards in the poker deck, and there are 52 total cards. So the probability of drawing a face card, given that we have a shuffled poker deck, is 12 out of 52, which is the same as 3 out of 13. Finally, we can summarize probability distributions just like we summarize data, using the mean, the median, the mode, the standard deviation, and the quartiles. In particular, we're often interested in the mean of the distribution. This is often called the expectation. The expectation is a weighted average of all of the possible values in the probability distribution, using the probability of each value as the weight. For example, if we look at the probability distribution of all of the 6 numbers that we could get rolling a fair 6-sided die, the probability of each is 1/6. So we take 1 and multiply by 1/6, that gives us 1/6. We take 2 and multiply by 1/6, that gives us 2/6. We take 3, multiply by 1/6, that gives us 3/6, and so on. We add all of these products up, and we get 21 over 6, which is the same as 3.5. So the expectation of rolling a fair 6-sided die is 3.5. Note that we can only take the mean of a distribution of variables that has an interval or ratio level of measurement, just as when we were computing the mean of data from a sample. The expectation is what you would get if you took the average of a very large sample from this distribution. For example, if you rolled a 6-sided die thousands of times and recorded the number of pips that came up each time, and then you took the mean of your thousands of trials, you'd get a sample mean that's very close to the expectation of the die roll, 3.5. The computation of the mean of a distribution involves multiplying each possible value by its corresponding probability. This is much the same as when we calculate the arithmetic mean of some data. For example, suppose we were computing the mean of these 10 numbers. To compute the mean, we add up the numbers and divide by the sample size, 10. But notice that this set of numbers has several replicates. There are 3 5s, 2 7s, and 4 8s. We could save some time punching in numbers into the calculator by remembering that repeated addition is the same as multiplication. Adding 3 5s together is the same as multiplying 5 by 3. Instead of adding up each of the individual values, we can multiply each possible value in the sample, 5, 7, 8, and 9, by the number of times that each appears in the sample, and add up the results and divide by the sample size. Computing the mean of a probability distribution is very similar. We take each possible value in the probability distribution and multiply it by its corresponding probability. The probability is akin to the number of times the value appears in the sample. Then we add up the results. We don't have to divide by anything because the probabilities in any probability distribution always add up to 1, and dividing by 1 doesn't change the result. With continuous distributions, like finding the probability that an apartment's rent is more than $1,000, things get a little dicey, since the number of possible outcomes is infinite. Exactly how to handle this is beyond the scope of this course. It involves calculus. But let's just suffice it to say that probabilities for continuous distributions come from the area underneath the distribution curve.